We're now at the point where we can formulate a computational problem that, when we solve it, will in turn solve the genome assembly problem. This first formulation won't be perfect, but it'll be a good starting point for our discussion of the assembly problem. Kind of in the same way that the naive exact matching problem wasn't perfect, but it was a good starting point for our discussion of read alignment. So the computational problem is called the shortest common superstring problem, which we'll sometimes abbreviate as SCS. So the shortest common superstring problem is this. Given a collection of input strings, a set of input strings, we'd like to find the shortest string that contains all of our input strings as substrings. So for example, here I have some strings, and I'd like to know their shortest common superstring, the shortest string that contains each of these strings as a substring. Well, if we didn't have the requirement that the superstring be the shortest superstring, then this problem would be easy. We could simply concatenate all the strings in the set S. So this is a string that contains all the input strings as substrings, but it's not the shortest. So it turns out this is the shortest common superstring. So this is a string that contains all the input strings as substrings, and there is no shorter string that does this, that contains all the input strings. So let's say for a moment that we have an algorithm for finding the shortest common superstring of a set of strings. And we'll discuss such an algorithm soon. So if we took our sequencing reads and we gave them to this algorithm and asked the algorithm to find their shortest common superstring, then the solution to the problem, the shortest common superstring problem, would also be an assembly of the genome. It would be a reconstruction of the original genome sequence. So let's look at an example. Here's our overlap graph from the previous lecture. So this graph is built from a synthetic data set that contains the reads that we made by taking all the 6-mers of the genome. And let's instead take all these 6-mers and then throw them into an algorithm that solves the shortest common superstring problem. So here I have some Python code that calls a function called SCS, which we haven't implemented yet, but we will implement in an upcoming practical. And we pass in a list, a Python list of strings, and those strings are the read sequences. And then what we get back is the shortest common superstring, which is shown here. And you can see that this shortest common superstring is, in fact, equal to the genome that we derived the reads from. Okay, so when we do that, we get the correct answer. So we should be pretty pleased with our progress so far. We've formulated a computational problem that seems to correspond very closely to the assembly problem that we would like to solve. Furthermore, this computational formulation has a nice feature. It's going to find us the shortest common superstring. Not just any common superstring, but the shortest one. And in some sense, this is like the simplest explanation, or the most parsimonious explanation for the set of input reads that we started with. And that seems like a good thing. That sounds like a good property to have. Well, so now, unfortunately, this shortest common superstring also has some substantial downsides. So we'll look at these and some potential solutions in this and in some upcoming lectures. So let's look at the first downside. The first downside to this problem is that it is just not tractable. There are no efficient algorithms for solving it. So the technical term is that the shortest common superstring problem is NP-complete. And NP-complete problems are very, very unlikely to have an efficient solution. This doesn't mean it can't be solved. In fact, we'll see an algorithm for solving it pretty soon. But it's not going to be very fast. And as the number of input strings grows, it's going to get slow very, very quickly. So let's see an outline for the sort of algorithm that we can use to solve the shortest common superstring problem. So let's say we have some input strings, and assume for a moment that they're all the same length. And what we're going to do is we're going to put them in some order, like this. Maybe these are our input strings, and this is the first order we're going to try to put them in. This happens to be alphabetical order. And then we're going to, for every adjacent pair of strings in this ordered list, we're going to find the longest overlap between them. So that is, we're going to find the longest suffix of the string on the left that matches a prefix of the string on the right. And then we're going to glue them together accordingly. We're going to merge them together accordingly. So for example, these first two strings in our ordered list overlap by 2 characters. The suffix AA from the first string overlaps the prefix AA from the second string. And there are no longer overlaps between these strings. So we glue them together like this. So we started with the first string, AAA, and then we tacked on just the B from the second string. Right? We ignored the overlapped characters because those are already in our superstring that we're building. And we just added on the B from the second string. Okay, so now let's look at the second pair. And again, they have an overlap of length 2 because there's a suffix AB for the string on the left, and there's a prefix AB for the string on the right. So this time we're going to concatenate just the A from the second string. So we're concatenating just one more A onto our superstring that we're building. And we can keep going like this. So for this third pair, the overlap is 1, right, because the suffix A matches the prefix A. So we're going to add on BB to the end of our superstring so far, and so on. We'll just keep doing this for every adjacent pair of strings until we've done all those pairs. And at the end of the day, we have a candidate superstring. It's not necessarily the shortest common superstring, but it might be. If we pick the right ordering, then it will be the shortest common superstring. So for a given ordering, that's how we produce the candidate superstring. And again, it's not necessarily the shortest. And for different orderings, we'll get different superstrings. So for example, here's another kind of order that we could put the strings in. It's just a slightly different order than the first one. And then through the same procedure, we'll produce a superstring. And lo and behold, you can see that it's shorter than the first superstring by, I guess that's 4 characters. It's shorter than the first superstring. So if we want to find the absolute shortest common superstring, we're going to have to try all the orderings. So that's our algorithm. For every possible way of ordering the n input strings, for every permutation of the n input strings, we're going to glue adjacent pairs of strings together according to their maximal overlap. And then the shortest common superstring that we get over all those orderings is the shortest common superstring overall. So why is this so slow? Why do I say that this problem is intractable? Well, this particular algorithm is slow because the number of possible orderings that we have to try is equal to the number of input strings. Let's say that's n. It's equal to n factorial because that's how many different permutations of n there are. So n factorial is a quantity that grows very quickly as n grows. So as the number of input strings grows, the amount of work that we have to do, the number of permutations we have to try grows very, very rapidly. That's why we call this problem an intractable problem. So in the coming practical session, we'll implement this idea, and then in the following lecture, we'll talk about one way that we can speed things up quite a bit, though at a price.